Hi, my name is Matthew Lachance. I have 5 years experience in SolidWorks and Fusion 360. I got certified associate 2 years ago, and I went to Stills, Ontario for mechanical CAD. I'm making this video for everybody in 162-inch graphics at Queen's right now because I think they glossed over some pretty important facts about the software. And I think that SolidWorks is in general a really valuable skill for engineers to have for design and for everything. Because once you're able to model anything that you're thinking of fluently and easily, then you can start to get into the more involved parts of SolidWorks like simulation and manufacturing and designing things to actually be built and creating drawings rather than just trying to fight the software to get whatever results that you want. So here's my certificate for SolidWorks, here's my certificate for skills, and this is a rocket that I built in senior year high school. The reason I'm showing you this is because this is kind of like the end product of CAD. This is something that I actually built, and this is something that theoretically would work. I have some video of it. So you can see that it was made through 3D printing, and it has a bunch of restrictions because of all of the electronics. It needed to fit the sizes, and the design part of SolidWorks is all about understanding how to design something based on the restrictions of your manufacturing or based on some kind of constraint and to solve the problem. But what we're concerned with right now is actually just trying to figure out how to model the parts, and then once you are fluent in being able to model something, then you can easily just apply whatever constraints you have to the modeling rather than trying to do it the other way around when you don't have a good basis for modeling in the first place. So right here I have a part that I've submitted for the Formula SAE team at Queen's. This is just a generic part. I don't really know what it does. And I want to take a sec to just talk about what SolidWorks is. So compared to something like Blender, Blender is really free. It's really relaxed with how you can do things. You can move things around. You can kind of do whatever you want. SolidWorks is almost the complete opposite. Everything is math equations, everything is based relative to this origin, everything is defined, it's all measured, it's all calculated, and these are really useful traits for your models to have when you want to design something to be accurate. So I'm also going to take a second to just kind of break down what are we kind of looking at here. On the left hand here, this is something called a parametric tree. It is actually a timeline which you can scroll through. So this is really useful because if you ever got a part and you didn't know how it was built and it's a parametric CAD part, you can scroll back in the tree and kind of scroll through it, and then you can understand how it was actually built by viewing the changes made to the features, which are derived from sketches in the viewport. We also have materials. You can find those here. You can edit them, you can make your own, you can import them, and they all have physical properties that are used in simulation. And then you also have your measurement systems on the bottom right. One thing I want to talk about quickly is selection filters. This kind of trips some people up. A good rule of thumb is when you hit S, this little menu pops up and you can look at almost any tool that you could have. And if you click this little I here, then it'll take you right to the tool. So selection filters are just used to select different things specifically. If I wanted to just select faces, then I wouldn't be able to select anything other than faces. I also want to briefly talk about part inspection. So if you go to evaluate, you have a measuring tape and you can measure anything you want. You can measure areas, you can measure diameters, you can measure distances between circles, etc. And this is really important to have because if you're at the end of your model and you don't want to go and check all the sketches, you can just check some key measurements and make sure that everything is aligned with your drawings. Also, you can click on mass properties and you can see the centers of area, the volume, the mass. Keep in mind that majority of the parts, if you're doing exams online or whatnot, they use mass and your material to determine if your part was modeled correctly. And this is because they don't have time to check the file itself, so they just check the mass to make sure all of your features were imported or created properly. And then if they are, then your mass should be the exact same because everything is math and it should all work out. Another key UI element is this eye up here. You can use it to toggle different things to view in your scene. Some really important ones are origins, your primary planes, different other planes, axes, and temporary axes, which are all of the invisible axes for any circular sketch objects or features that you might have in your scene. Something else is the movement is really bizarre in the sense that the bottom plane seems to rotate around pretty freely. A good tip is never use trackpad with SolidWorks. That is just bound to cause frustration and just annoyance. I'd recommend a 3D mouse or probably just a mouse just to start. So if you click and hold middle mouse, you pan up and down, and then left and right is left and right. but through rotating it, you're actually rotating your part. I just take like 5-10 minutes to get familiar with this so you can have a really tight control over your part, and you can kind of look at things really easily. Because if you're trying to even fight what you're looking at, then you're just not going to have a good time with anything else. So make sure that you can intuit everything pretty easily. One more thing that I also wanted to touch on would be, what is somebody that is a modeler versus a designer? So modelers are people who are really good at modeling things in the software, but people who are designers are able to apply all of the modeling techniques, but with restrictions of manufacturing that I talked about earlier. And as engineers, we want to be designers because we are trying to make things that are adapt to physical conditions, different manufacturing constraints, different clearances, what kind of tools we have available, the prices that we're trying to meet, and all of that comes from designing. But it's kind of the blending of modeling and engineering, which is what we want to get to. But again, before we get to that, we got to learn how to model, and then we can start doing simulation and other complex processes to actually understand the geometry we're creating a little bit better. Okay, let's start modeling a part. So we're going to unhide our planes. That's usually a pretty good place to start. We're going to check that we're in millimeters. We're going to define our material, just something generic, 1060 alloy. And then we're going to select this top plane. And let's understand first what something being defined means. What does it mean to have measurements? So if you select this circle, you'd think you'd be able to come over here and you'd punch in your measurements, but that doesn't work. Even though you define it here, that's not how you properly define something. You're going to want something called the Smart Dimension tool, which actually creates measurements in the software. If we tell this, if we make that 50, center point on the x-axis, 50 from the origin, that means it is always going to be 50. No matter what else happens to this circle, we can drag it, we can scale the radius. It is always going to be 50 from the origin. And the goal is to lock out all of these dimensions. We want to make sure that this circle, there's no uncertainty with where it is, how big it is. Now the software, it turned black, and we can't really do anything. We can't drag it. It's defined in space. It has a defined radius. We know for certain that this circle is following these measurements. So dimensions are really good, but when possible, always try to use geometric constraints. Geometry, eventually when you create more complex parts, geometry is going to have to reference itself. The best way to make sure that your model will update properly is to add these relations. If we wanted to make this centered, sure, we can define both of them just with dimensions, but you can also shift click the midpoint and then shift click your origin and make it vertical. And now, no matter what happens to this, it's always going to stay centered. So now if we can define it once, and we'll say it is 100. But that's kind of weird. Why did these ones get defined and this one doesn't? But when I was first learning it, I didn't really understand it. It's because this one can still move up and down. So when you're looking at it, you should really be looking at these points. Those points are still free to move up and down, even though they are constrained to 100 millimeters in width. We can pull these down a little bit. Another good rule of thumb is to just click and drag any points you want, and then that'll tell you how it's underdefined. We'll make our arc on this side, actually. We'll make this too. And notice how everything went underdefined because I deleted that line, and now I also deleted some of the geometric constraints. We're actually going to make this coincident, and now we're going to try and define stuff relative to that. So the other geometric constraint making these horizontal also disappeared, so we're going to correct that. We're going to make this arc tangent, and we're also going to define this relative to the origin as well. And let's make it 145. So now we have some kind of geometry. It's pretty generic, but it can be updated pretty well because it's really defined by only two things. If this wasn't tangent, we could have defined the radius separately, and we could have defined a bunch of things separately, but now the model will update pretty well. But let's get into some extruding. We're going to extrude this out, and we're going to make another sketch. We're going to do it on this side, and I'm going to try and go kind of quick here, just because I'm trying to get to something else. Notice how we're not even we're 2 features in, and I'm already referencing stuff from other geometry. So another really useful tool is this convert button. You hit it, and you have the edge from the 3D geometry projected into your sketch. So this is actual sketch geometry now, but it comes from this edge. And what that means is that if I was to take this sketch and change it, 150 50. That means that this sketch updates as well. That geometry stays the same in this sketch because it's referenced to that edge. And that's a really important thing to know, because if all of the geometry was underdefined previously, then that wouldn't be defined either, and then the model might not update properly. And that's really the power of SolidWorks, because now we can actually reference other geometry and the model will update according to the dimensions that we put in. So let's go back into our other sketch, and we're gonna make basically the same part. And we'll just kind of sketch this out pretty quickly. We're going to make this construction geometry, meaning that it's not going to influence our features because we're just going to redraw this line. But what's interesting is that that line is coincident with that line, so it shares its definition. We're going to make sure these are tangent. And we're going to make sure this is horizontal. And this time we're going to define based on the midpoint, or the middle point of that circle, and it's going to be maybe a little shorter, 50. And now we can define that. And let's, I don't know, you probably wouldn't do this, but we'll define it based on the midpoint, just so we only have one dimension. And now that dimension is controlled based on how long this is. We're also going to make another circle in here, which is going to be concentric. And we're going to create since they are concentric, we can just define that width pretty easily, and it's always going to be maybe a little smaller, 20. Or maybe we shouldn't do that, because now that's relative to that, and if we want this hole to be a constant size, then that means if this were to expand, like if this was to change to like 200, our hole would also get bigger, and we might not want that, so we're going to try and make the hole a constant size. So instead, we want this hole to be a constant size, so that's why we're going to give it a dimension of 35 millimeters, and then we're going to just extrude this. And quick primer on end conditions. So there's multiple different kinds of end conditions. This one's a blind, which means it's just extruding a generic length. Then you've also got through all, which means it's going through the entire model. And this one's the one we're interested in though. It's up to surface. So we can select any surface and it'll extrude up until that point. We're going to make another sketch and we're just going to make like a generic cutout. And if we hit space and we go on to there, shift select the top of this edge, convert that over, make it construction geometry, make this collinear with that edge. Let's go 10. And let's also add another line. This is going to be another construction line because it's going to be our line of symmetry. 1, 2, 3. Symmetrical constraint. And now that's all defined through all. There we go. So now we have a pretty generic part. Best practice is to usually save all of your filleting to the end. Maybe we want to make a couple fillets. And another good idea is to do fillets in multiple steps sometimes. So maybe we'll have these ones as being 5. And we'll make some of our larger fillets 2.5. Okay, so not a bad part, but we're going to make another part because we're going to make an assembly. And if we know this diameter is 35, then we're going to try and 3D print this assembly, just so we know how, I guess. So that diameter is 35. So a good rule of thumb might be to make it a millimeter smaller, depending on the fit. This is something that can be really finicky sometimes, so you might have to just figure this out for yourself through multiple prints or through some other guides, because on another note, you can add equations into the box right here. So we'll do 35, subtract 1, and then remember that we're not working at then we're going to extrude. We can tab back over to our other part. So that's around 100 millimeters. We could have probably told from the sketch, but I don't really want to go searching for it. Nothing's on the other side obstructing it, so we're probably just going to extrude it like 100 millimeters blind. And for fun, let's give this thing like some funky features just so we can see how lofts work. So I'm going to actually suppress our fillets, which means that I'm essentially going to hide them, but it's like just getting rid of the feature for now. And we're going to create another plane. And sure, 50 is good enough. We're going to make another sketch. So lofts are pretty advanced, but we're just messing around, so we'll just see how they go. We're going to make a slot, then we're going to define the slot, 20, define its length. We'll make it relative to the back instead of just a fixed length, so then it'll update with our model a little bit better. We're going to say the center of that circle should always be 50 millimeters from that back wall. And you can start to understand why this might be a problem, because if we ever changed our width to somewhere over here, where this measurement isn't possible, actually, let's do that really quickly. I'm going to make this loft, and then we're going to try that out just to see what happens. So loft, 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 and it creates really smooth geometry. And you can always add guide curves because you notice that the interpolation is very linear. You can always add guide curves, actually. That's how this part was, actually no, yeah. You can always add guide curves along the sides to actually change that interpolation along the part, but that's kind of out of the scope of what I'm trying to show here. So you can look into it if you want. What would happen if we made our sketch a little shorter, where that measurement just wasn't possible, like 10. So our entire model is going to blow up. See, all of our features are no longer possible. Because if you look, this sketch is now looking like this. Maybe I should be a little nicer to this part. And we'll say it's like 75. So some of the features can get made. And what the fuck? Okay. So you could see when we updated our part, the diameter of these circles stayed the same, this got shorter, and this got pushed even further in. So you can kind of you can start to understand how changing your part in different ways will alter the actual model, and your relations matter quite a bit. So now we're going to try and make an assembly out of these two parts. So we're going to go in, we're going to put our bracket down, and notably, we're going to treat this bracket like our origin. That's why it has that F. It's fixed. We can also float it if we don't want to, and we can like drag it around, I guess. But we're going to make, but we know this one needs to be static, so we're going to fix it, and we're going to insert another component. That's going to be our bracket. No, it's not. It's going to be our dowel. And now we can start getting into mates. Mates are a really cool feature in SolidWorks because it's essentially just like defining a sketch, but you're figuring out how different parts slot together. If we selected this circle, mate them, and that created a concentric mate. So now we can know that these circles are going to be concentric no matter what, but it's still underdefined because it can move back that way. We don't really want that. We want it to just be able to go in circles. So another really good mate to know is the width mate. You essentially select both of your widths, and it'll perfectly center the part every time. So if this part ever updated to where it was wider, that ensures that that part is going to stay centered in the width. So you can see how it's still able to spin, and that's exactly what we want. So let's create just another part, generic part, that'll lock onto that, and we're going to go as fast as we can. So we're going to obtain the measurement between here. It's 80. We're going to make it like 79 because we don't want it to be brushing. We don't want it to be brushing up. Okay, so now we're going to make another part really quickly. I don't know what's happening with my views. So we're going to take a measurement of our dowel, which we know to be 34, and then we're going to go back over here, make this the radius, 34 divided 2. We'll make this a little thinner too. It would be kind of cool if it lofted out. I'll explain what that kind of means in a sec. And this, make it like that. So 17, we make that coincident. And this is going to be that represents the dowel. And then we can offset this with this tool, offset. And we'll say, because we're going to be 3D printing it, we're going to want it kind of bulky. If our print head is only 0.4, then that means it can only extrude like 0.4 in like a sphere, I guess you could think about that. I'm not really too sure how to explain it, to be honest. So first we're going to make our offset though. It's going to be 1 millimeter, so that's the amount of clearance we're going to have between the dowel and the part, and then we're going to make the actual thickness of the part, and we're going to say that's just going to be like around a centimeter for fun. And oh, I can't get rid of that. I can't really get rid of that now. That's a kind of another weird way of defining things. Yeah, I really shouldn't have made this rectangle to start, so this is a pretty bad sketch, but we'll just kind of go with it, and we're going to make some cool features with curves, because curves always look nice. We're going to make this one tangent, and we're going to also make it tangent to this one, and then that should almost carry it. That should almost fully define it. We're also going to make this symmetry line so we don't have to do everything, or it can be infinite length, whatever. We're also going to make the symmetry line so we don't have to do things multiple times. Make it symmetric. It didn't like that. I think it's because the radius needs to be like curved inwards first. So, symmetric. We'll try that again. There we go. And we have control still of how much curvature we want it, how far we want it down the part. So I guess we're going to define this relative to the end, and we're going to say it's going to be like maybe 100, and then we get some decent curvature still on the part. Make these construction as well, and we'll just redraw it, I guess. Who cares? Very messy sketch. Definitely wouldn't have started with this rectangle in the future. If you really want, you can use trim, and you can kind of trim away some of the circle, so it's like cleaner, I guess. You don't have to. That's really a preference thing. I like keeping all of my sketch geometry messy just because it like shows me all this stuff, but I don't know, whatever. So then we select this, and then we're gonna make it the width. So that's a distance of, I don't know why that's in meters. What the fuck? Okay, so if we remember this length, it's 80 millimeters, so we're probably just gonna make it like a millimeter less, maybe, or millimeter or two, doesn't really matter. We'll see, we'll be able to see how it fits together once we get it into the assembly. We'll just try like 78 millimeters. Yeah, it does have closed contour. Select our contour. There we go. Insert components. Insert from the other document, not the dowel, the arm. And those sketches are kind of annoying, so we're just gonna hide that sketch and we'll mate it. Same as before, concentric mate. And then we're also gonna make another width mate. And that's another thing. The width mate is independent of your clearances. So if we were to make this like a coincident to the face, and then with some kind of offset, we'd have to change that every time because of the clearances. If we ever made it smaller or bigger, then it would be always hugging that wall, but the width makes sure it's centered. So that's good. And this is free to spin around. I don't really know what we've made, but we certainly have. So if you really wanted to, you could define some kind of angular, so we could say this needs to be 45, and then now this assembly will be 45, will be fully defined, because there's that angular mate keeping it in place. I'm not really a fan of that, because I want to see how this thing is actually going to move, and you can kind of see how it moves. You can also run, under evaluate, you can run interference verification, so we can make sure that this dowel and this are not touching within. And we can see all the clearances. You can see there's 1 millimeter of clearance there, and that's pretty useful to see if any of your parts are touching or if they're clipping into each other or whatever. And there's plenty of different other things you can do. Interference, clearance verification, you can do design studies, you can... Alright, one more thing, we're going to talk about some basic 3D printing. So when you're 3D printing something, you want to usually export it as an STL, because remember that SolidWorks this is like pure math right now. It's all calculations. We need some actual real geometry. So we're going to make a mesh file, an STL that's just a bunch of points and it's a bunch of faces. It's what's in Blender actually. That's what this thing could be. It's basically an STL. This is what a mesh looks like. That's what it's going to make. So we're just going to call it just an assembly, I guess. And this is what the mesh looks like. You can see how it's creating all of its triangles. And we'll say yes, create the thing. We're going to pull it into the slicer. I have a bamboo printer, so we're using Prusa stuff for 5i. But this is like the same fundamentals. It doesn't really matter. I just want to kind of introduce some quirks to 3D printing stuff. Yeah, so here's our assembly. We're just going to click drag them. And here it is. It's pretty big for the printer, so let's just pretend that I modeled this to scale. And we're just gonna like scale it down a little bit. Here it is. Nope. Okay, so something to consider with 3D printing is that everything is made in layers. So if I was to slice this right now, which is to turn the model into just a bunch of layers, then this is kind of what it would look like. But it doesn't really... You can kind of tell that geometry would be pretty impossible to make because of the overhangs. Because if you're printing, like, and you get to this point here, where you have to make an overhang like this, that's like 90 degrees, then the slicer just can't do it because you can't extrude all of the material because it prints layer by layer. So it prints all of that and then it goes layer by layer. And it's so you need to orient your parts and design them such that they can be printed from top to bottom. So that is one of the constraints for 3D printing. You can auto-orient it, but we're going to print it as multiple parts because we designed it to be assembled. Click off it. We're going to take this and we're going to lay it flat on its face. Lay on face. We're going to pick that one. Dowel. We're going to pick this and we're going to pick that. We're going to lay it down like this. And oh no, that's worse. You kind of got to figure it out. Bamboo thinks we should orient it, yeah, like that. And then we're going to have to generate some support in, although it might not be necessary because the overhang is at an angle. So when it's progressive, there's a chance that it could, but just to be safe, we'll put support on it, which is like, you can think of it like scaffolding for your 3D prints. So if I had something like this and then we rotated it like that, and we sliced it. So it's creating the scaffolding because you need support there to help the 3D print so it has something to print on for that overhang, and the same thing is happening right over here. And here are some important elements. Your material, I believe we're printing in PLA, which is just some generic plastic. Other materials that you might see are carbon fiber. This is very, very strong tensile material. I think it has like 15, so yeah, it's like 5 times stronger than steel. Very strong material, very common to work with, UV resistant, and have some other cool properties. Your nozzle also is very important because this is how much material you're actually extruding. So if we were printing this with a 0.6, then our slicer also gives us plenty of information about how long it's going to take, how much material it's using, and you can see all the different steps to creating this, and you can start to understand where your time is coming from, spending on infill, how much is spending on travel. So you can get really into optimizing these models based on like the strengths and the surface patterns and how much infill they have, which is just like the scaffolding inside the part, how dense it is with plastic, because printing it solid plastic wouldn't really be smart because you basically get the same level of strength from just the scaffolding. You use less material, prints faster, etc. You can dial in all the speeds, you can change all the supports, different kinds of supports, and you can change the different qualities, the layer heights, the heights of the layers, the seam positions, because this is where all of the layers end. You can think of it like that. So as soon as it goes around all of these different points, it has to end there, and that can influence like the quality of the print in some ways. Different positions. I don't really mess around too much with these options. You can also change the layer heights themselves, and that's not really important for prismatic stuff like this, like that or that, but it's important for stuff like this where there's curvature. So you kind of have to decide whether you can also make adaptive layer heights, so it'll change the layer height once it gets here, once there's curvature, or you just have it all the way through, but that's kind of out of the scope. I don't know. There's plenty of stuff you can research for this, and it's really good to understand what's actually happening when you're printing the part and how you can print them faster, how you can save material. Also, a quick introduction to drawing, some of the other things that you could do for that. You can select like your assembly view and you can make it shaded and colored. You can change the scales down here, and then when you actually want to make like a model view of the assembly, double click that, and then you can drag it in here. We're going to change it to use a custom scale. It's going to be 1 to 12 like the other one. And we're going to make this one 1 to 5 as well. And something important to remember is that this follows all of the same rules of... So now we're going to also make some drawings. So after we have like our main views imported, we can click the views to make more. And it follows all of the orthographic rules from our drawing. So you can also double click them and you can change the scale. You can make them shaded known lines. You can see the hidden lines, basic stuff. And then under annotation is where it really gets cool, where you can start adding center lines. If you wanted to make that a center line, you could add center marks. So if I wanted center mark on that circle, you can always add dimensions to tell people specific things about the model and how it was dimensioned. Some rules of thumb. Don't ever try not to cross your dimensions as much. Try to keep all your dimensions off the model. They shouldn't be intersecting, and always try to keep as few dimensions as possible. But if you're ever in doubt with if you should include a dimension, you should always just include it, because it's just a pain in the ass if somebody has to figure out what that dimension is instead of just looking at it when you could put it in. And you just kind of go and you define your model. Yeah, pretty simple. You can make different things like bills of materials, different kinds of views, like detail views if you really wanted to show off this circle. And then you can see that up close. You can make section views where you can see the... Sure, I don't know what it's trying to tell me. And then you can see like the cross sections of different parts. So you can get really into some of this drawing stuff, and I don't really care for it, but it's pretty cool, and it's definitely useful to know, especially when you're interpreting other drawings. So now let's look at some extra resources that you can use to help study or help practice or whatever. This is something called Model Mania. SolidWorks does it, I think, every year. I don't know. They have 20 years worth of parts just to try, and it's really specific to the software. So you can try and design all these different parts. You can see how this one kind of has a loft, it has an extrude, some curves in there, and you have to do it using only these dimensions. And this is basically what the CSWA or the certification is based on. So practicing this stuff is always really useful. And then what's also really cool is you go back and you have to make changes to the model, because you're never going to get it right first try. So you need to see how well your model adapts to these changes and how easily you can make them. And then you can always time yourself and see how fast you can be. It's always just fun to treat it like a speedrunning challenge. You can get really fast, and if you don't know how to model something, there's always videos included. You can go through and you can kind of watch it and see exactly how somebody else would do it. So the last resource I wanted to share with you is the CSWA practice exam. This has tons of just really good, solid questions. You can download like a wizard for it if you really want to, and then you can answer some multiple choice. But what we're really interested in is the part modeling section, where they give you a part and they tell you basically just model it. Here are all of your dimensions, and you need to model this part. This one looks like it's really sketch heavy with just one extrude. Then they tell you the dimensions of some of these variables. Then you have to modify the part by changing the variables, and then you have to actually make some other changes to the part by changing the variables again and making some extra features. And then there's some assembly stuff. Nobody really cares. There's answers included. Very good resource for practicing. And then one more resource that I actually used when I was learning SolidWorks is this one service called SolidProfessor. If you're willing to put down some money, or if you know somebody that has a professional license with SolidWorks, sometimes this is included. And even though you have to pay, it's really cool because all the tutorials are built around getting you to... Basically, the final exam for this is getting your certification. So it's a really cool way to learn the software, and then you actually get something to show off that's endorsed by SolidWorks. And yeah, I think that's about it. Thank you very much for watching. If there's any questions you have, feel free to leave them in the comments below. Yeah, I'll try and link as much stuff I can in the description. I'll try and make myself available if you would need some one-on-one tutoring or whatnot. And thank you very much for watching, and I wish you all the best with learning SolidWorks. Thank you. Take care.